guys, welcome back to another episode of Pollys Introduction to Computer Networks. So what are the announcements today? I think the only thing that you want to pay attention are just the assignments due this week. PA2 will be due, and hopefully 3 quizzes will be assigned this week. Okay, and hopefully you'll be, oh hi, Elona, sorry, your name is really hard to, so Elon, okay, maybe. So hopefully 3 quizzes will be assigned and you'll be able to complete them during the class. All right, so what are the topics today? Yeah, we want to, hi Jeremy, hi guys, good to see you too. All right, so hey, a quick recap of last week. We talked about the core of a network. Okay, there are 2 principles, okay, designing such a core of networks. One is CS, the other PS. Hi Isa, hi Sylvain, Miguel, Maria. Hello to you all. What is CS? Hi Ji. Oh, Zach. Hi. Okay, good. Enough greeting. What is CS? Counter-Strike? PS? PlayStation? Okay. Yeah, you feel that Polly is a little bit playful today. No, seriously. CS? Circuit switching? PS? Packet switching. And internet. Okay, so much of what we'll be talking about this semester, starting from now, will be internet, the computer network, okay, or sometimes called data network. And internet is operated under this packet switching principle. It's a packet switched network. Okay, so at the end of the lecture last week, we talked about packets. Why don't we send large file at once, but to cut a big file into smaller packets? And you see an example, right? Because we can then pipeline smaller packets. Okay, as the first packet traveling the second hop, the second packet can go on the first hop. The initial delay will be much lower. And that is a major issue with the packet switching network. So we have to send smaller packets. But at the end, I also mentioned that if you send 2 small packets, it's also not good because there's this thing called packet header. Those are in the packet header part of the packet. Those are just control messages. Those are not real data. Only the payload, the body part of the packet, carries the real data coming from the end users like this. So if you send like 1 bit of data every time, then you have many bits overhead and just 1 bit real data. The overhead is also very high. So you want to find a packet size that is just right. And how? Well, it depends on the link bandwidth. It depends on also let me see. I think it also depends on the usage, okay, the user demand. So that's a tricky problem, right? Now, there's a little bit more I want to talk about packet switching. In that principle, there's a key phrase we heard, store and forward. Okay, what that meant is that we'll have to store the entire packet and look at the content in the packet before a router can decide where to send the packet next. Okay, but why? Okay, why do we need to store the data entirely? Okay, and this is what this video is about. Okay, store and forward. And why do we need to store packets first before forwarding it, right? This is one of the reasons that we still need to form packets. Why we cannot just streamline the bits. The reason has something to do with how the routers is working. So inside the router, there are 2 key functionalities, and there are 2 of these. First is routing. So there's some sort of algorithms there. The routers, given the graph of the network, computes the shortest route. At the end of it, we generate a routing table like this, a forwarding table like this. And the way we look up this table is by matching the destination address, okay, of the packet. And so if a packet comes into a router, inside the router takes the destination address in the packet and look up this table. If there's a matching entry, the router discover what is the next router to forward to, what is the right direction to pass this packet further. Okay, you see, router what? Oftentimes well connected to other routers on the internet. So this router here could have multiple ways of passing the packets further. Unlike the very simple scenario there, each router has only one outgoing link, right? So it's no longer that intuitive why packets need to be stored and then forward. Now you see, packets need to be stored here, and then the router can look up this field and match this entry and then discover, okay, this packet is supposed to go out on network interface 2, this direction, to this router next. Similarly, this router needs to store the packet entirely, and then it can look at the header, this particular field, destination address, and find out in its own routing table which router next to forward the packet. Yeah, it's exactly because of the forwarding functionality that's required to pass data around over a packet switch network like internet. So on packet switch network, we store packet before we forward it. So forwarding here is to move packets to routers all the way from the source, eventually reaching the destination. Right? We'll definitely tell you more as we come to chapter 5. Okay. So in datagram network or in data network, the way it works is let's receive a packet entirely, okay, and look up the destination address to determine which is the next hop. And so you see, if the routing table change, if the graph change, routing table would change. When the routing table change, when the forwarding table change, yeah, the subsequent packets might be following a slightly different path to the destination. Okay. So the routes, packet traverse might change in a session, in a data stream session. So the analogy here is that packet switch network is a little bit more like the regular car network. Okay, if we are driving a car, a lot of times, hey, to find out the next segment, okay, which road segments we should go on, we might actually stop and pause and ask someone for this destination, for direction, or park to the side and then look up Google Map to find out which is the next segment. All right, so that was why we need to store and forward. But as you can hear, that means for every hop the packet travel, it's extra delay. Okay, good. So I see a question from Eleanor. Elon. Okay, I'm gonna play the next video while I read your question. Okay, and the next video is this. So you see that there's a delay at every hop. So packet switching people actually thought that maybe we can try to emulate that reservation behavior in circuit switch network in packet switch network. And that thing is called a virtual circuit. So we implement some sort of virtual circuit in packet switch network. So this video, 3.5 minutes, telling what VC is and to give you a summary, okay, of all the taxonomy. And actually in a packet switch network such as internet, we can potentially emulate a circuit-like behavior that is called virtual circuit network. So instead of looking at the destination field in the packet header, we look at a very special header field called the virtual circuit ID field. Okay, so there is a tag there, carries a number. Okay, that number determines which is the next hop. So inside a packet, there could be many fields in the packet header. One is called destination. There's another one called the virtual circuit ID. And one can look up that field and decide which is the next hop. And how do we do that? We'll talk about that also in chapter 4 and in chapter 5. And what's nice about this approach is that we can then try to ensure, okay, all the packets for that stream traverse a fixed path. In a way, packet number 1, 2, 3, 4, chances high that they arrive in order. In this case, in case routes might change, if the later route is shorter than the earlier route, chances there packet 1 might arrive after packet 2. So, packet switch network. To sum everything up, this is general communication network. Two different flavors depending on which philosophy we design the core of the network. If we are going for a circuit core, it's called circuit switch network. If we are going for a packet-centric core, packet switch network. In circuit switch network, we know there are different ways of dividing resources into pieces. Frequency division or time division. But either way, it's very regular following certain order. Things will need to be reserved. There's a call setup delay. It's good for long-lasting calls where you will prefer data not experiencing variation in delay, not experiencing losses. But this is very resource consuming. Each time we will not be able to allow many users going on at the same time. On the other hand, packet switch network, simpler, flexible, no idle resource, but we might have congestion. So that's this track, datagram network. We look to the destination network address and then decide which is the next hop to forward. And so we need to store the entire packet, and so they might get queued. And they might get dropped in case there's not enough space in the queue. But we can also try to emulate a circuit behavior using the virtual circuit tag, which allow us to look up into the packet header field that's a little bit faster and streamline the process more or less and maintain packet arrive orders. Packet switching versus circuit switching. All right, so that's the end of packet switching versus circuit switching. We'll have to talk about one more thing, because the internet is a network of networks. The next two videos coming up are to give you a visual sense, okay, of how internet looked like. First one is how internet looks like in the past and why, okay, it has evolved to today. The second one is to give you a better sense how they look a lot more messy in the modern days. But before we start with the videos, let me come back to Elu's question. Thank you, Elu. So it appears that there could be multiple routes of packet travel. How does one decide, right, given a packet, which way to go? That's a very good question. On internet, there's one way the packet go, and only one way. And that is determined based on this thing called the destination address on the packet header. And how do we know given the destination address? So destination address will be the receiver's IP address. Okay. So the sender side sends packets given the destination IP address. It's almost like sending a letter to your friend. Writing on the letter, that envelope is like the packet header, and the address of your friend is just like the destination address. And there's going to be a mechanism inside the internet determining, okay, how that letter gets passed on and on. And you might be surprised that it's very similar to the postal system. Think about the postal code. Yeah, so by looking at the postal code, you kind of guess, right? This the destination is in a particular city, and inside the city a particular area. Yeah. So it's deterministic in internet. On a circuit switch network, then it's usually a specific circuit ID. And therefore, virtual circuit there is to try to use an ID. And so for virtual circuit implementation of packet switching, inside the packet, then you will see a header field called the virtual circuit ID. And that is the thing that the router uses to decide which is the next router. Okay? All right, so let's check out how the internet looked like in the past and why it has evolved over the years and the shape has changed drastically. All right, great. Internet structure. It's a network of networks. Earlier we learned we have end systems at the edge of the internet. They're connected to the core through the access networks, which are part of these access ISPs. Now, some of these ISPs serve home users more. They're called the residential ISPs. Others serve companies and universities. They are more often being called institutions and ISPs. Well, either way, any two hosts in these ISPs wanting to send packets to each other, their access ISPs will need to be interconnected. As a result, we see a network of access networks. Over time, they grow pretty large and complex. And much of these growth is driven by the economics, and some of it driven by governmental or business policies. In the next few slides, what you'll be seeing is essentially the evolution of the internet. What I'm drawing here is a bunch of these access ISPs, or I call access nets here on this figure. Let me just omit drawing the end systems because there's just going to be too much of them and the picture gets too messy. So the first thing the internet engineers are thinking is this: how are we going to interconnect these guys? Well, one obvious way is, how about connecting them all? But as a result, you see there are n square connections. And when the internet grows, adding one more access net, we'll need to add n extra links. So this is going to be a very expensive thing to maintain. And so internet engineers go with the other extreme. Everyone connects to one global ISP in the middle. So data come here, and the global ISP transits the data for the access net to the destination. Similarly, here. So in a way, the global ISP in the middle here is providing transit services to the access nets, which are the customers. Now, as the internet grows, as the number of these access nets grow, then there'll be more paying for the transit services. Gradually, the global ISP will begin to see profit. And when business is profitable, you see competitors. So now we have not just one global ISP, but multiple global ISPs. So A, B, C here are three global ISPs. They're competitors, but unfortunately, they also need to collaborate. Because what? Just like the access nets needs to be interconnected so that they can serve the end systems, their customers. ISP ABC will also need to interconnect so that they serve their customers, the access nets. All right, so must interconnect. There are two ways for the global ISPs to interconnect. First is to establish peering links among each other. The other is to connect through these IXPs, Internet Exchange Points. Now, these IXPs are special. They're typically set up by government fund or by the nonprofit organizations because it's kind of important that we have these, third company there maintaining the basic operation of the internet to avoid companies, commercial companies, to dominate. So that's pretty much the structure of the internet for a long time. But over time, we see more. So local communities such as this guy and this guy here can also grow. When there's enough number of these access nets around, we begin to see regional ISPs showed up. What these regional ISP is doing is this: offering lower price internet access to the access nets and try to negotiate internet access with the global ISP with a lower price. So hopefully the regional net here finds a margin of profit. So profit here and saving money here. For global ISP, this might not be a bad thing at all because it only needs to deal with one customer, which is the regional ISP, instead of multiple of them. Okay, so less overhead. Yeah, so makes sense. Okay, pretty much like how a major business is growing to the global scale, isn't it? Yeah, the second video here is modern day internet. There's this thing called content provider network. They're supposed to be the edge, but nowadays, in terms of how much users they have, they are actually higher in hierarchy, okay, in terms of revenue profit. And this structure has been there for a long time until about a decade ago. Content provider networks showed up. Let me talk about content provider network by example. So let me use Google here. It'll be easier for you to understand. So Google established these data centers worldwide. Okay. What they do is to go to access networks locally where the data centers are, and then ask to connect to the access network, their data center. Now, the number of machines they are maintaining there at their data center and the connections they are buying from the local ISP are actually comparable to the global ISP here. The entire infrastructure there at the content provider network is just as big as the global ISPs in the middle. But what's a bit odd is this. The content provider networks, they're actually physically at the lower level of the hierarchy. As opposed to the global ISPs, they are at the center of the hierarchy. Scale comparable, but where they are in the hierarchy, very different. All right. In the next picture, let me try to draw the network slightly differently so that you see where they are in terms of how resourceful these provider networks are. You see here then, the most resourceful one at the top, the least resourceful one at the bottom. Okay. So at the center, we have Tier 1 ISP and content provider network. Tier 1 ISP interconnect to each other through peering link, and they also connect to the IXPs. Content provider network somewhat different. They connect to the local access ISPs and IXP. All right. But keep in mind, this is not exactly absolute. Some Tier 1 ISPs might also have access ISPs connections. Google here, if this Tier 1 ISP offers a fair price, might also establish a connection. All right. Good. Now, the final slide is just to give you a rough idea what's inside a Tier 1 ISP. As I'm drawing here, it looks simple, but it's actually quite complicated. This is Sprint's backbone. Sprint is one of the major operators in the US. It's also a Tier 1 ISP. Each of these red dots is called a POP, point of presence. So the role there is pretty much like a data center in Google. It's a rack of machines In this case, a rack of routers. Okay, so rack of these routers. They're interconnected between each other, and they are also offering connections to the customers. And some of them might be connected to other tier 1 ISPs. And these links are to go further up into the backbone, in the hierarchy of the backbone in Sprint's network. And this is internet structure, a network of networks. Okay, yeah, it's quite messy, isn't it? It is. Okay, so messy is the key word of how internet look like in terms of its structure. Now we move on to the next topic. That's chapter 1.4, performance of the internet. Okay, you see that the internet is still advancing, and we hope that the packets can be sent or data can be sent faster with little loss, with higher throughput. So we have these metrics. I just mentioned 3, okay, that evaluate the performance of the internet. So this first video, it's not quite, we are not yet ready for delay, but the first video should be an overview of the 3 metrics. Starting from here, we'll focus our discussion mainly on the packet-switched internet. And 1.4 is to talk about the important metrics we care about designing protocols for it. That includes delay, loss, and something called throughput, which we'll talk about at the very end of 1.4. How do loss and delay occur? Well, let me draw your attention to the example below that a bit easier. First kind of delay is happening here, in the packet that is going out, being transmitted out. That delay the packet is experiencing is called the transmission delay. That is the time it takes to transmit the packet, and we know how to calculate, don't we? It's packet size divided by the link rate. But there's a second kind of delay experienced by packets here before they get to go out. These are what? Packets waiting in a queue, waiting for its turn. And how can there be packets waiting in a queue? It actually happens quite often when the incoming rate exceeds the outgoing rate. So you see in the example, A and B sending packets actively together into the router. In case the aggregated arrival rate is higher than the outgoing rate here, then you will see there will be always packet here waiting to be transmitted, and therefore subsequent packets will need to what? Wait up. And that is queuing delay these packets are experiencing. Now the calculation of queuing delay is a lot more challenging than the transmission delay. It really depends on the arrival pattern before a packet comes into the queue. Okay, now if that pattern is reoccurring, predictable, then it will be easier to calculate this. Otherwise, very challenging. Now, that explains packet delays, where they might occur. Packet might get lost as well at the router, and it happens here. Focus on this thing here. It's the packet queue. The size of the packet queue is limited. Okay. By the way, that packet queue is also often referred to as the buffer. Okay, and the buffer space is limited, just like the memory space is limited. The buffer space is just a way of calling the memory reserved, okay, to store these packets. Now, given that the amount is limited, in case congestion persists for a long time, then eventually you run into the situation. There's no longer free buffer space in the queue. In that case, arriving packets will get dropped, and therefore we see packet losses. Yeah, I think many of you probably feel that, hey, we are picking up the lecture speed a notch. Okay, I hope that it's okay. Yeah, we do want to go a little bit faster. All right, so those are the 2 major metrics, delay and loss. There's one more called throughput. We'll go through each one of these next. And first is delay. Yeah, although I say delay, but there are actually 4 components, 4 kinds of delay. And this is what this video is about. Now, packet delay. There are 4 components. The first component is the nodal processing delay, but we just call it processing delay. It occurs right here when the packet arrives at the router. Router here checks the bit errors in case there's any, and decides quickly which output link the packet should go out. Next, queuing delay. That's the time the packet waits until it's turn to go out on the output link. So it occurs right here at the buffer space where packet queued up. But the amount of wait depends on the congestion level of the router. Component 3 is the transmission delay, and it's calculated this way. R being the link bandwidth, L being the packet length. And the time to transmit the packet out will be L divided by R. And it's happening right here at the interface between the router and the link. Final component, propagation delay. Provided the length of the physical link and the propagation speed of signals traveling the physical link, we know that the propagation delay is D divided by S. So essentially, the time for the packet to traverse the physical link. Be careful. S here is the distance the signal can travel per second. R here is the number of bits the transmitter can push out per second. Although I call S the propagation speed, R the link speed sometime, but there are two very different quantities. All right, so let's exercise how to calculate the transmission and propagation delay through two examples. Right. Now let's go through a couple examples to exercise calculating transmission delay and propagation delay. What you're seeing here is a caravan of 10 cars. Now the way to think of this scenario is this. Think of cars being bits and caravans being a packet. So we have a packet containing 10 bits in a sense. The cars will be propagating at the speed of 100 kilometers per hour over 100 kilometers, reaching the second booth. Toll booth number 1 here takes 12 seconds to service the car. All right. Question here is asking how long until the packet is lined up before the second router. All right, so transmission speed, transmission delay plus the propagation delay. So what is the transmission delay? We have 12 seconds serving per bit, and then there are 10 bits. So the time to push the entire caravan out of the toll booth is 2 minutes. And then the propagation delay is for the car to travel 100 kilometers. So 100 kilometers dividing the propagation speed. So we have 60 minutes here. And so altogether, 62 minutes before the entire caravan to reach the second toll booth. So you see, in this case, transmission speed, very fast. Propagation speed, slow. In the second example, the configuration is slightly different, mainly propagation speed and transmission speed. Propagation speed now goes really fast, but transmission speed much slower. So question here is asking, will the first car arrive at the second toll booth before all the cars are being serviced? Let's see, when will the first car arrive at the second toll booth? So transmission delay, 1 minute. Propagation delay, so we have 100 kilometers, but we're traveling 1,000 kilometers, so we'll be spending 1/10 of an hour propagating, and that's 6 minutes. Together, 7 minutes. So the first car will spend 7 minutes before arriving at the second toll booth. Now, 7 minutes is also the time to service 7 cars for the first toll booth. That means we have 3 cars that are still behind at the first toll booth. So yes, okay, when the first bit arrives at the next router, there could still be bits not yet transmitted out from the previous router. So in this case, where the propagation speed is really fast, transmission rate very low, you had this weird situation. Yeah, so generally when the transmission or the service speed is low, you had a higher chance seeing a queue. Okay, good. And the next video is to sum things up, the 4 components of delay. And Polly will point out that which of the component there is the hardest to compute. That is called the queuing delay. Good. Let's sum up packet delay. So there are 4 components: processing delay, queuing delay, transmission delay and propagation delay. Transmission delay, very low, typically microseconds. We just ignore the processing delay when we calculate packet delay. Transmission delay, propagation delay, very easy to calculate. L divided by R, this quantity is often significant and especially the case for low-speed links. Propagation delay, slightly harder. It varies quite a bit from microseconds to hundreds of milliseconds. So this extreme is for satellite links, for example. We've seen earlier, it could go up to 200 or even more milliseconds. Sometimes the transatlantic or trans-Pacific links, very long optic fibers, could also take up to 100 milliseconds. Now, in the process of calculating packet delay, the hardest component is this, queuing delay. Now, it's very hard to calculate accurately because it depends on the congestion level at the router. Just to give you a sip of how hard it is, let's define again, R being the link bandwidth, L being the packet size. Let's add one more variable, the average arrival rate. So L multiply A is the average bit arrival rate. That is also the incoming traffic rate. R is the outgoing traffic rate. So we could define traffic intensity being LA divided by R. So when that quantity is close to 0, that means incoming rate very low, outgoing rate very high. Then no bits really need to wait. So queuing delay very small. And it's depicted here. When LA divided by R is very small, queuing delay also very small. The other extreme is here. When the intensity is greater than 1, that means there are more bits coming in than more bits going out. And when time goes on and on and on, the newly arrival bits will need to wait longer and longer and longer. And it's pretty much here, approaching infinity. Now, when the intensity is between very small to 1, delay is simply growing. And as we will be approaching infinity, you see that the curve grows quickly like that, okay? Close to an exponential trend. So, hard to estimate queuing delay. In fact, it takes a whole semester for a professor to teach about how one calculates queuing delay. And at the graduate school, there's advanced queuing delay that one can also take to make sure that you do a better job. Okay, estimating queuing delay for highly dynamic incoming traffic. All right, so that was delay, the theory side. Now, Polly is gonna tell you about this utility tool on Unix systems in general. Sometimes you will have to install it. It's called traceroute. And this utility program is very often used to measure delays, delay from hop to hop, okay, from router to router. So that's what this video is about 5 minutes. All right. So that was the theory part of the packet delay. One can also find out what is the real internet packet delay by trying out this program, traceroute. Okay. What it does is to measure delay from a source 1 hop at a time, all the way to a destination. So this is what I'm drawing here. Source to destination. And it's sending 3 packets, 1 at a time, to reach each of the routers along the way. So router there, receiving such a packet, would return by sending a reply back to the sender. Now, the sender there can time the interval between the transmission and receiving the reply and gets 1 estimation of the round trip time between the sender to the router. So it works like this. 3 probes to the first router, 3 round-trip time estimation. 3 probes to the second router, 3 round-trip time estimations to the second router. And this goes on and on until it reaches the final destination, and then the traceroute program stops. The output of the program looks like this. This is an example. Trace routing from Gaia, umass.edu to Oracom, France. So this is saying first hop router's name is cs-gw at IP address 128.something.something.something. And there are 3 round-trip time estimations, 1 and 2 milliseconds respectively. What's a little bit interesting is between hop 7 and 8. There, you see at hop 7, round-trip time was about 22 milliseconds, but suddenly to hop 8, the delay is about 100 milliseconds. So that is the transatlantic links connecting from US to Europe. A little bit more interesting is also hop 17 and 18. You see stars, stars, stars. That means the routers are not responding. Okay, and it could be because the probing messages are lost or the replying messages are lost. But it's more likely that the router is turned off replying to these. Routers are on, but the routers turn off replying these probing messages. Well, let's try, sending a trace route ourselves from here. How about that? Let's go over to a terminal and then trace route to say Google. How about that? All right. Good. First hop router. Well, it didn't tell me the name of the router, so chances high that the router doesn't have a name. Okay. Delay reasonable. 10 millisecond, 3 millisecond, and another 3 millisecond. Router 2 here, well, either the probing messages are lost or router turns off the functionality of returning to trace route probes. Now third hop, 30 milliseconds, suddenly much higher. Okay, fifth hop, delay not much higher than the third hop. And you see here, when it's star, 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 it takes longer time. It's because when the traceroute program sends the probing packet, there's a timeout interval. Traceroute will wait until the time exceeds the interval. Then it determines that, hey, the router is probably not going to respond anymore. So forget about the first probe, send the next probe. Next probe waits also some amount of time. Timeout, give up, and then sends the third probe. Okay, good. Finally, we reached www.google.com, but the name is actually quite different. TSA something something. Interesting. And the end-to-end delay, end-to-end round-trip delay to www.google.com is about 20-something milliseconds. Now, something that's very odd is here. Hop 8. If you look closer, we do have 3 round-trip time estimates, but each time, number A here along the way, the 8th hop, is slightly different. IP address is 101, 49, and 97. So you see here, packets, although going to the same destination, coming from the same source, as they go on the internet, the routes could actually change. Also, you see, hey, the time it takes to reach hop 5, 30 milliseconds, but the time it takes to reach hop 12 is only 20-something seconds. So the load of the internet changes also over time. So sometimes when you are probing to a closer router, could take a longer time because it was busier there. But when the traffic load drops and when you're probing a router that are farther away, you could get a shorter round-trip delay. Yeah, very curious. And let's go back to the slide. And it turned out that it's a good time to start the next quiz. And here we are, okay, the quiz. By the way, guys, and this is gonna be your first take-home quiz, okay, meaning, okay, question from Miguel, trace route, exactly. Trace route in Windows is just trace RT. Okay, good point. Thank you, Miguel. So this is the first take-home quiz because in order to finish all 3 queues, there's not enough time. We have only 5 minutes remaining. Okay, so let Polly describe the quiz, and you guys will take the quiz home, okay, and work on it. So this is quiz number 6, okay, and this is the exact trace we've examined, okay, in the videos earlier. So it's output of a trace route probe to this server, Oralcom.France. And Q1 asks this: how come the 3 delay measurements are not quite the same? And if you pay attention to this very last video, you should know How come the three measurements are not quite the same? You see, 1 millisecond, 1 millisecond, 2 millisecond. 16, 11, 13. But this is coming from the same source to the same router in the middle somewhere. So why? Okay, and Q to ask this. How come some delay measurements to hop 10 are longer than the delay measurements to hop 11? Hop 11 is supposedly farther away from the source, right? And supposedly delay should be longer, but if you see here, hop 10, the second measurement, 121 millisecond, the delays to the 11th hop, to the 11th hops are all shorter than 121. Why? Okay, and last one. So traceroute is a program that we use to find out, right, if there's a bottleneck, a certain hop being problematic on the internet. But it is also often used to try to estimate the delay between two hops. Okay, for example, between 3 and 4, between hop 3 and hop 4. Okay, can you use these readings to estimate the delay between hop 3 and 4? And can you use the same mechanism there, you estimating the delay between hop 3 and 4, to estimate the delay between 8 and 9? Oh, you want to be careful, right? You see that, hey, 104, 109, 106. Overall, the delay to hop 8 is longer than delay to hop 9. Yeah. So an obvious mechanism you use here might not work here. So guys, spend more time thinking about the mechanism you use to estimate the delay using traceroute. And this quiz here will determine whether you win the extra bonus, okay, for quiz 6. All right? And you know what? Good timing. It's 2:07. For some of you, if you want to stay on and work on quiz 6, feel free. And I can also take you to W3 quiz 6. Okay? And you guys can have a quick chat. And if you arrive to a solution quick, feel free to post the solution there. Okay? And you know what, guys? With that said, I say goodbye. So we end the lecture about 2 minutes earlier. Okay? Bye. That's all. See you tomorrow.